Let's now work out an example and see how we can put everything together in a real, almost a real life example. So let's assume we want to pump oil. So it's expected to pump oil with density 800 kilogram per cubic meter and viscosity 0.08, 0.008 kilogram meter second. This is dynamic viscosity along a pipe of length 100 meters. Diameter of the pipe is 1 meter, and it's expected to, let's assume the topography is like this, right? So we want to pump the oil basically uphill from here, right? So it goes uphill, all right, like this, and then there is a valve here, and this is basically where we want the water or the oil to basically be used. Or for example, it goes to a refinery or so. So the total length of the pipe is 100 meters, diameter is 1 meter, and then we have a pipe. We know the loss coefficient for the pipe, KL, for the valve is 0.5. Okay, and it's a dimensionless number. Okay, perfect. So the question is, okay, what is the pump head needed to be able to achieve a volume flow rate of Q is 1 cubic meter per second. 1 cubic meter per second of flow rate. This is basically the flow rate that we want to achieve. Okay, so we start by writing the energy equation. Energy equation basically says P1 divided by gamma plus alpha 1 V bar 1 to the power 2 over 2G plus Z1 is equal to P2 over gamma plus alpha 2 V2 bar to the power 2 over 2G plus Z2 plus HL. That's a total HL. Okay, now let's start by rearranging this a little bit. So P1 is the pressure here, P2 is atmospheric pressure. So really P1 minus P2, what we're looking for, it's the pump head, right? So I'll bring the P2 on to the left-hand side, and I'm going to get P1 minus P2 over gamma. That's basically what we're looking for. That is equal to alpha 2 V bar 2 to the power 2 over 2G minus alpha 1 V bar 1 to the power 2 over 2G plus Z2 minus Z1 plus HL total. Now let's work out every term, like terms one by one. First is the kinetic energy, right? And this has to be given to us whether the velocity profile at the outlet is the same as the velocity profile at the inlet. So the assumption is D is uniform across the pipe. And let's assume that velocity profile is also the same. So therefore, if velocity profile is the same, diameter is the same, then V bar 1 is equal to V bar 2. And because velocity profile is the same, well, V bar 1 equal to V bar 2 is because the diameter is the same and volume flow rate is the same. And because the velocity profile is the same, then alpha 1 is equal to alpha 2. And therefore, there's no change in the kinetic energy of the flow from the inlet to the outlet. And then the valve, we assume is fully open. All right. Good. So the second term is Z2 minus Z1. So the height difference. And the height difference, let's say it's 1 meter. 1 meter. So therefore, this is simply 1 meter. And then we have to calculate the head loss. Now, head loss total has two terms. HL total is HL major plus HL minor. Okay, so in order to calculate HL major, Remember here, we don't have tau W, and we don't have delta P, but we have velocity, average velocity. Basically, average velocity is Q divided by area. That's Q divided by pi d squared divided by 4. So it's 4Q divided by pi d squared. Q is 1 cubic meter per second. Pi d is 1 meter to the power 2. So it's basically, if I'm doing everything right here, is 4 divided by pi. All right, if I bring the calculator, so it's 4 divided by pi equal to, and that's 1.27. So I'll put this here. So that's going to be equal to 1.27 meter per second. All right, the reason I'm calculating V bar is I want to calculate the Reynolds number. So let's see what is the Reynolds number. So from here, we conclude that Reynolds number is rho V bar D over mu. Rho is 800, V bar is 1.27, D is 1, and mu is 0.008. The 8 and 8 goes away, so then that's 100 divided by 10 to the 2, 10 to the negative 3. That gives me 10 to the 5, right? Times 1.27. So the answer is 127 with 3 zeros, or as you can see here, 1.27 times 10 to the 5. That's a Reynolds number. What do we do with the Reynolds number? Well, as we said before, we have to use the Moody chart to get the friction factor. So 1.27, remember the Reynolds number is on the x-axis, but x-axis is logarithmic. So this is 1 10 to the 5, and this is 2 to the power, 2 times 10 to the power 5. So 1.27 is somewhere here. The exact value doesn't matter. Now, usually the statement of the problem has to tell you if it's a smooth pipe or it's a rough pipe. So let's assume that it's a smooth pipe, and I'm going to add it here. So it's a smooth pipe. Okay. So therefore, this is a line for a smooth pipe, and let's see roughly what the number is. Well, so this looks like to be 0.017. Okay. So therefore, from here, we conclude that friction factor is 0.017, and that is equal to delta P over 1/2 rho V squared times D over L. And you can basically read this from the Moody chart. This is the definition of friction factor, D over L times delta P over 1/2 rho V squared. Okay, so therefore, we're looking for delta P, which is the friction factor times 1/2 rho V squared times L over D. And in fact, we're looking for delta P over rho G, so I have to divide it by rho G, and I can get rid of rho and rho. So really what we're looking for is F V bar squared divided by 2G times L over D. We already know that F is 0.017, V is 1.27 to the power 2, 2 times 9.8, L is 100, and diameter is 1. So let me bring the calculator here, and let's see what we get here. So I have 0.17, nope, 0.017 times 1.27 to 7 to the power 2, okay, divided by 2 divided by 9.81 times 100, and that is 0. What was the number? Did I lose it? 139, so 0.14. So this is equal to H loss major. Okay, so H loss major is equal to this number. I'll just put a box about it. Okay, so that's the first part of our H total. So this term is calculated. Now let's go and find out HL minor. So looking at the problem, we have one valve with a KL equal to 0.05, and I can try to squeeze the solution to that part here. KL is HL divided by V2 over 2G. So therefore, HL is KL times V2 over 2G. So in this case, HL, therefore, HL is KL, which is 0.5 times 1.27 to the power 2 divided by 2 times 9.81. Bring the calculator again. Okay, so what do we have? We have 0.5 times 1.27 to the power 2 divided by 2 divided by 9.81, and that's going to give me 0.04. All right, and this is meters. Everything for head, everything is meter. So the H loss minor is equal to 0.04 meter or 4 centimeters. So it's not huge, but again, if you have a large number of these guys, then of course they're going to add up. Okay, so therefore the H total, we can just substitute the numbers. We have equal to 0.14 plus 0.04 meters. So the total is 0.18 meters. All right, and that goes back here. So that's going to be plus 0.18 meters, 1 meter, and this term is 0. So therefore the total head needed is going to be 1.18 meters. All right, so I can just write down the final answer. HL total therefore is equal to is it HL? No, I'm sorry, the delta P total. Delta P over gamma total is going to be 1.18 meter. So we need a pump that can pump water 1.18 or 118 centimeters up, and that pump is going to achieve 1 cubic meter per second flow rate inside the pipe that basically goes uphill 1 meter and has a valve with a loss coefficient 0.5 in it.